If I could just have a few moments just to kick things off here, and then we'll let people munch away. Can people online confirm that they can hear me?
I can hear you.
Okay, great, excellent. Okay, so we are slightly changing. I think one of our speakers is running a little late, so we get to hear from Maggie first. So Maggie is over at Columbia University, and Maggie, why don't you quickly introduce yourself, and then we have about an 8-minute talk with 2 minutes for questions. So it's going to be a little rapid fire, but if you have more questions, I'm sure Maggie will be around to answer those in the chat. So, all right, Maggie, take it away.
Sounds good. Thank you. So my name is Maggie Powell. I'm a PhD student at Columbia University in the Earth and Environmental Engineering Department, and I'm also a Department of Energy Computational Science graduate fellow. Today, I'll be talking to you about 3D radiative effects of cloudy atmospheres using high-performance computing on Perlmutter. But in general, I am an atmospheric scientist who likes using computational methods. And for this work, I was advised by my advisors, Professors Pierre Gentine and Robert Pincus. I'm sure there's many modelers in the room, and as modelers, we need to make approximations. And so a commonly used approximation for atmospheric radiation is to neglect the horizontal transfer of radiation and to compute fluxes only in 1D, in the vertical dimension, using independent vertical columns. And there are a number of biases that arise from making this approximation. Sometimes we call these 3D radiative effects. And today I'll be looking at shortwave 3D radiative effects for surface fluxes. So this is the difference in the average 3D versus 1D surface fluxes of sunlight at the surface. And these effects can be substantial, especially for broken cloud fields, such as deep convection and shallow cumulus clouds. So I know not everyone is an atmospheric scientist, so I'll give you a brief introduction into 3D radiative effects. So downwelling shortwave radiation or sunlight at the Earth's surface is made up of direct or unscattered and diffuse or scattered fluxes. And we have 3D effects for both. So for the 3D direct fluxes are typically smaller than the 1D fluxes. When we make this 1D approximation, the sun is always directly overhead the clouds, even as the solar zenith angle increases and physically the sun is getting lower in the sky. Whereas in 3D, when radiation can transfer horizontally, the shadows are displaced and stretched. Bigger shadows mean less direct flux. For diffuse, we see another effect. The 3D diffuse fluxes at the surface are larger than the 1D fluxes, and this is because of something that's sometimes called side leakage. Because the scattered radiation can leak out the sides, it's more likely to reach the surface than if it was forced to remain within its cloudy column, where multiple scattering means it's more likely to be reflected up out of the domain. So we have these two competing effects of different signs. We know that these 3D radiative effects exist and we understand some of their mechanisms, but we wanted to investigate them at scale. And that's where Perlmutter and HPC comes in. And we want to do this for a large number of realistic high fidelity cloud scenes. By having that large sample, we can ask science questions such as how much of the global or the net 3D radiative effect can be explained by differences in direct radiation alone, as well as many other questions. But I started this talk by talking about how we're making this approximation. We made that approximation because calculating 3D surface fluxes are expensive. Well, the way we get around this is by using some fast code and NERSC GPUs. So we do our shortwave radiative transfer calculations using a Monte Carlo ray tracer from a group at Wageningen University. And this is a statistical method for solving the 3D radiative transfer equation. And the code is written in C++ and CUDA. And we calculate the surface fluxes for a large number of high fidelity cloud scenes from a data set called the Cloud Botany Catalog. So this is many members of many large eddy simulations of shallow cumulus clouds. Picture tiny popcorn convection over the ocean. And it's for a large domain, 150 by 150 kilometers at 100-meter resolution. So just to give you a sense of the scale of this calculation, for one cloud scene running with 128 samples per pixel at the top of the domain, we're doing this 3D radiative transfer calculation for 3 times 10 to the 8 samples. And on the GPU, that runs in less than 4 minutes. So what does that look like? Here we're looking at the surface fluxes for one scene and one set of solar zenith angles. Starting on the left side of the screen, we're looking at the direct or the unscattered surface fluxes for the 3D calculation. The sun is at 40 degrees from the zenith, and it's coming from the top of the page here. And just to give you a sense of how large these domains are, we're going to zoom in to just the bottom corner and look at a 25 by 25 kilometer portion. So first, comparing the 3D versus the 1D direct fluxes, if you look closely, you can see that for the 3D, the shadows or those darker areas are displaced and they're also stretched. So that's what I was talking about before, where the 3D direct fluxes are lower. Now, if we look at the diffuse, I think this is where we can really appreciate how when we allow for the horizontal transfer of radiation, things are much smoother. Whereas in the 1D approximation, all of the scattered sunlight is falling directly within the cloud shadows. And it's hard to tell with your eye here, but in general, the diffuse fluxes are higher in 3D. And then something that's really interesting about the spatial distribution of these fluxes is in 3D, we have some of the highest values falling just outside of the cloud shadows. And these surface fluxes can be hundreds of watts per meter squared higher than the fluxes you might get on a clear sky or a cloud-free day. And that's because you have the joint contribution of the clear sky flux, or this green if we look at the direct field, and the diffuse flux or the diffuse enhancement. Whereas in 1D, the max value is equal to the clear sky value. Okay, but that was just one scene. We're going to take about 100 cloud scenes, and for each one, we're going to do this in an offline setting, and we're gonna move the sun around, sampling multiple solar angles. So moving the sun down from the zenith and changing the azimuth or the polar angle. So in the end, we have more than 400 3D radiative effect calculations. And what do those look like as a function of solar zenith angle? So here we see this tug and pull between the diffuse and direct effects. So starting on the left side of the plot, this is when the sun is directly overhead. The 3D and the 1D shadows are the same, and so there's no direct 3D effect. But the diffuse effect happens regardless, and so we have a positive global 3D radiative effect. As the sun gets lower in the sky, those shadows are stretched, so we have an increasingly negative direct effect. And the diffuse radiation also gets higher in terms of the net effect because there's more scattering and more intercepted sunlight in the 3D scene. But as the sun gets lower, ultimately that shadow stretching wins out and the net effect changes in sign from positive to negative. When I was thinking about this talk, I realized that I didn't have quite enough time to go into some of the science, but I'll just give you a quick preview. By having such a large sample, it really gives us room to develop and test idealized models that allow us to ask and answer fundamental science questions. And without going into this plot, that's what we're doing here. So in conclusion, we used a GPU-enabled Monte Carlo ray tracer to compute 3D radiative effects on surface fluxes for shallow cumulus scenes. And those effects are negative for direct radiation, positive for diffuse. And if you want to chat more about the science, if you're in atmospheric science, please send me an email, and it's listed here. Thank you, and I'm happy to take any questions.
Are there any quick questions in the room, or let's see? Any questions online? Okay, if not, thank you again, Maggie. And as you saw Maggie's email address, definitely connect with her if you want to chat further. Okay, why don't we go ahead and move to our next remote speaker, Xuping.
Okay, yeah.
Sorry, I hope I didn't mispronounce your name, please.
Yes, that's right. Okay, so let me,
great.
yeah, let me share my screen now.
Yes, please.
So can you see my screen, everybody?
Yes.
Okay, all right. So, okay, let me start. So, thank you so much. Thank you, Lippy, and also the LERSC organizer for providing this remote session so that I have a chance to talk about my research work and today. And this is today, I'm going to talk about this latent space dynamics learning for Steve CR model. This is a project supported by the FES, DOE FES program. And also I did this work, this collaboration work with Professor Chi Tang at Georgia Tech, and also Dr. Xianzhu Tang, and he's the lead PI of this project and at Nano. So I did this this project with them while I was a postdoc there. Right now I'm a junior assistant professor at the Department of Mathematics and Statistics at Old Dominion University. So I'd like to, so this, I'd like to make this apology first.
Can you make your slides in presentation mode just so they're a little bit bigger? Thank you.
Okay, so yeah, I mean, first thing, the work is supported through the DOE FES machinery and AI program. And second, I mean, of course, this work, I mean, used the resource of LERSC. And so let me first give you a brief background about the CR model, the collisional radiative model. So this model, so the CR models is a very important processing in plasma simulation. So those models can describe the atomic process in a plasma by tracking the population densities in the ground and the excited states for each charge state of the ion. So then in the plasma simulations, the disruptions can occur when the plasma field becomes unstable. So these instabilities can lead to a sudden loss of confinement and causing the plasma to touch the reactor walls. And so in that situations, that's a big, I mean, those instabilities can cause severe damage to the reactor. So that's one of the very important challenge. That's one of the big challenge in fusion, I mean, control. So to prevent the severe damage, we need to accurately predict the ion population distribution and the radiative power cooling rate before a disruption occurs, so that we can take some actions. For example, propose some control and mitigation strategies. So that's a very brief general background for the CR model. And actually, so there are just two processes in this CR model. The first is the auto-ionization, so from the atomic physics level. So this process occurs when an electron in a high energy excited state undergoes a decay that leads to the emission of a photon and potentially ionize another electron in an excited state. So I think you can take this is the first figure, just clearly illustrate this process, this auto-ionization. Another is the electron capture process. So basically, for the ground state, the ground state can capture some electron to become high energy level. So those are the two very basic processes. I mean, that happens in a plasma field. So for this, describe the CR model. And so if we convert this into a mathematical model, so we can have a very high dimensional stiff ODE system. So where the dimension in real plasma simulation, the dimension is order of 10 to 6. This is a very high dimensional system. So then a high fidelity model is computationally intractable in an integrated plasma simulation. For example, a high fidelity CR model needs to be solved on a fast time scale at each grid point in an MHD simulation at every time step. So some very like inaccurate low fidelity model exists. So, but its fidelity is not enough for the need of high fidelity fusion simulations. So, this figure just presents a typical CR solution, CR dynamics solution for one species, the Lisider. So the overall dimension is 94, and we have 4 charge states. So as you can see from the solution, right? So this is it is stiff and it requires time steps following an exponential growth. If you look at the time scale, it's very small. Like and especially there's a fast transition of all the states. I mean, happen around at 10⁻⁷. So the scales in both in time scales, in time steps, and the densities span multiple orders of magnitude. So this brings the motivation of the ML AI-based surrogate models. So we need to propose a more fidelity CR model can be used to enhance data-driven ML models. So eventually we want to couple the CR surrogate model to the real dynamic plasma simulation to predict some real-time, right, to make some real-time prediction and control. So that's a goal for this project. So in our work, we propose a gray box latent space. So this contains two parts, and again, two components. One is the white space. So this is something referred to the part of the latent space composed of physical quantities that are directly interpretable and have well-established meanings within the CR model. So, and for example, so there's a coronary equilibrium model, so those physical quantities are represented by the charge state distribution. And by incorporating these known quantities, we ensure that the essential physical properties are retained in the reduced model. So that's the definition of the white space. And the black space, this represents a portion of the latent space learned by the machine learning model. So in this case, we use the autoencoder without direct physical interpretation. So there's no physical meaning for the black space. So the low-dimensional representations capture complex patterns and relationships not easily described by known physical variables. I mean, generally we know that this functions as a black box, like for like neural network-based autoencoder. So the green space refers to the combination of the white space and the black space. So this figure just demonstrates the overall architecture of the model that we proposed. So basically, we apply there are two stages. We first define the latent space. We perform the latent space reduction, applying autoencoder, standard autoencoder to get the black space, and then we concatenate our white space, which is a known physical information, and then we develop the flow map neural network to learn the dynamics under the exponential time integrator under the under this very fast tiny time scale. So so in the training, so we also enforce some constraint. One is the radiative loss rate, because we want to ensure that our neural network model can is able to predict the radiative power, the radiative cooling rate. Another thing is we enforce the total mass conservation as a weight constraint in the loss function. And also, so that's in the dynamics prediction stage. So we apply this the autoregressive model. So basically, we input the initial condition to the model, and then the model will iteratively predict the whole dynamics, the whole trajectory of the system. So that's And there are several key components in the training. One is that we did a subsampling in the training because there are two advantages for this. One is we want to reduce the total number of training data. So far, right now, we have 14.8 million pairs of training data for one species. So, and we're currently we're currently collecting multiple species. So then which will have larger, more data set than this, basically. So that's one of the advantages we want to do the subsampling. And another thing is we want to move the target flow map away from near identity mapping for very small delta t. So as you can see from the figure, so for those identity mapping, it's hard for your neural network to learn those identity mapping with a very small delta t. So that's the motivation we want to do this subsampling. And another thing is we need to apply some proper transformation for both time and time step and the density. So previously I mentioned that the time step scale ranges from 10⁻⁷ to 10⁻⁴, and we map this into a proper range between 0 and 1. The same thing for the density transformation. So, and another thing we did the very initial brute force search for the neural architecture. So we try to find an optimal neural architecture that can give us the best training results. And also, this team is still actively working on replacing the simple search with the ML-assisted advanced search for the neural network architecture. And so, basically, we separate the training, so the data into the training and testing. So under different parameter settings, because we're going to testing our model on some parameters that has never been seen, and that is anything to the neural net model. So this is the numerical experiment. So basically, so this we got an external agreement is external agreement is observed for neural model predicting dynamics of different parameters. So those, as I said, those are the training data set, or those are the testing data set. So those parameters, those data, are so those parameters are assigned to the neural network. So we get a pretty good prediction. And the same thing, so we got a good reconstruction for the radiative loss rate. And as I said, this is a very important quantity that we need in the CR model. So also we discovered the impact of the training data set. So we did two, during our first training, we used very small, we selected some small temperature values in our training data set. And during our second attempt, we used all the temperature values in the training data set. And the results tells that, so if we do not feed enough data, and then the prediction is not good. So the model cannot actually capture the dynamics. And then if we use a full data set, basically we need more, we feed more training data, so then we can get a very good prediction for the dynamics. So overall, that's my talk today. So I mean, this is still ongoing project. I'm still collaborating with the scientists at Nano and the Georgia Tech. So we're trying to propose some multi-time step prediction scheme for this work. And thank you so much. That's all for my talk.
Thank
any
you.
questions?
Thank you so much. Okay, normally we would have a little bit of time for questions, but in this case, what I'll say is if anyone does have questions, if they could email Xuping directly, because we're gonna move to our last quick remote speaker, give everybody another moment to stretch if you need to before we continue with the rest of our in-person presentation. So Beste, is that correct? Beste?
Yes, that is super correct. Hello.
Yes, okay, great. All right, take it away. Thank you so much for being here.
Thank you so much. Sorry for the delay in the first part. Hello, everyone. Everybody can see my screen, right? I guess so. Okay. So I'm Beste. I'm a third-year PhD student from Boston University. And today I'll share my recommendation framework for HPC batch job submissions. And so this project is in collaboration with Sandia National Labs, and I will share some of the motivations first for the intelligent resource allocation. On the left-hand side, I included a very simple batch job script that we provide to BUSCC, Shared Computing Cluster, in which we have the project name, job name, and some of the details for the requested resources. It can be the maximum memory, GPUs if we need, and the wall clock time limit. So from the user perspective, we are making these requests based on best to our knowledge. And the workload manager in the corresponding HPC system, such as Slurm, Grid Engine, Fujitsu, or the Altair PBS, they allocate the resources that we are asking for the duration that we need. So why do we care about allocating these resources more efficiently? Well, there are two main problems that are associated with the manual selection. The first one is if we request less than we need, we experience early job terminations and the overall system efficiency is reduced. On the other hand, if we are asking for more than we need for multiple batch job submissions, and if we are especially using the same batch job script to submit different jobs over and over again, we observed increased job waiting time, and at the end, the resources, compute and memory resources, are allocated unnecessarily. So our goal here with this recommendation framework is to optimize compute and memory resource usage in HPC systems by addressing these two main problems while enhancing the quality of service and preventing early job terminations. So I will first move on with the design of the framework. This is the big picture consisting of the offline model training and online resource recommendation parts. In the offline model training, we are using real-world workload manager logs, and we are training offline machine learning models to predict the resource requests of batch jobs using the submission parameters. So these submission parameters are the batch job submission parameters that I have discussed in the previous slide, and it changes based on the workload manager that we are working with. And in the online recommendation stage, we designed it such that we provide real-time resource requests to users before their jobs are queued. And lastly, we evaluate the framework success on deployment for a real-world HPC system. And right now, this system is Beste University Shared Computing Cluster, and we aim to apply this framework for other systems like Perlmutter as well. So let me move on with the offline training methodology. We are using similarities among previous job submissions from the historical data, and we create subgroups using the submission parameters that we have. So these historical data, they contain successful and failed job information. But for the model training, we are only using the successful jobs, and this is in the data pre-processing stage. And we label and code the categorical columns before we make any clustering and predictions. After separating the training and testing data, we first k-means cluster the jobs based on their submission parameters, such as username, job name, and requested resources. And we choose the resource type that we want to train our models on to predict. This can be the execution time of the job, number of cores to request, or the maximum memory size. In the testing stage, for the offline testing part, we first find the cluster based on the k-means model that we train, and we make predictions using the pre-trained machine learning models. So in the offline part, as I've said, we are using the real-world workload manager outputs to mimic the real-world deployment. And in the next slide, I will share the strategy to actually use it in the real-world HPC system. We collaborated, as I've said, with Boston University Shared Computing Cluster and Research Computing Services. And we modularized our training and testing code using LMOD. LMOD is a popular environment module system. And we have the accounting data from Boston University Workload Manager as inputs to the training code. Our outputs are the resource request suggestions for the user's new batch job submissions. So there are three main commands that the user should run in order to use this framework. The first one is, as any modules, we first load the module. It's called qsubrec right now, and 1.1 is the current version, which will be updated as we keep deploying the framework. And then we advise the users to run the training code at least once after they load the module. The model training saves the models to their home directory. So once they do this stage for the upcoming job submissions and request suggestions, they don't have to retrain the model for a certain amount of time. And then running the qsubrec script, we first load the user's prediction models and encoders, and we also receive the batch job script path from the user. This is the original path that they are using in order to submit their batch jobs. And we are making predictions on the requested cores or other resources and create a new file by adding the rec script name for the original name, and we print the results. So after this stage, the user has the option of submitting their original or the recommended batch job file to the system. And I also want to mention the low overhead and accessibility of this framework. With the users that we have collaborated with, we observed that the training time is less than 3 minutes, and it is definitely less than the login node time, which is up to 15 minutes of computation. And any user on the BUSCC system can use this framework for model training and getting the suggestions for their batch jobs. There are also 3 different comparison points that we care about, and these are actually our motivations to use this framework in large-scale computing systems. The first one is the wait time reduction. And we observed that for a neurophotonics application, which was requesting 8 cores per batch job previously, The framework suggested 3 cores instead. And for over 2,000 job submissions, we observed that the average waiting time has been reduced from 17.5 hours to 1.2 hours. And secondly, we also observed for another electromagnetic simulations application, the total CPU time is reduced by requesting less number of cores for their jobs. And at the end, overall, by making more informed resource requests, we observed decrease in the job turnaround time as well in multiple use cases. So our goal is to use this recommendation framework on a larger scale, which consists of a job grouping-based resource prediction stage and the recommendation framework for online batch job submissions. And again, to emphasize, we are using historical job information to have more efficient use of compute and memory resources. And this framework is flexible to be extended to other production HPC systems because of its modularized deployment. If you are interested, I have included the QR code for the paper, which has the preliminary results and the details of the machine learning part of this framework. And I would be happy to receive any questions, feedback, and collaboration through my email. Thank you.
Okay, wonderful. Thanks so much. Yeah, I think we're gonna skip questions just to give everybody like a minute to get up, move around, stretch before we move into the rest of the talks. Beste, thank you so much for joining us, and to all of our remote speakers. One more round of applause for our remote speakers.
Thank you. Thank you for the opportunity.